Hi everybody, welcome to the Introduction to Energy tutorial. This is module 3.1 and this is the first tutorial of the fourth 9 weeks. It's always nice to take a second and go through the objective just to let you know what we're going to be shooting for here. In this lesson we're going to try to explain conservation of energy as it relates to living things in different ecosystems. Conservation of energy of course has to do with the first and second law of thermodynamics, so we got to spend a little bit of time studying physics. Normally I skip over these questions and these assignments, but I want to take a minute to cover this with you. Yes, these are assignments. Yes, you have to do them. If you are looking at your tutorial grade and you see a 0 and you're like, but I did the tutorial, it's because when you finished the tutorial I went and looked and all you did was go through the tutorial, you didn't actually do the assignments. This is one of the assignments. It's a very simple thing. How would you define the term energy and why do living things need energy? You can try to describe it in your own terms and answer the questions in your own way, or you can kind of go do a little bit of things looking up. But I want to see you complete these assignments. And as you can see at the bottom here, there's actually a sample answer that I get to see. And why not? I'll give it to you. Energy is the ability to do work, and I want you guys to know that. Energy is the ability to do work. Now, when you think do work, you mean like get up and go to work? No, I'm talking about anytime anything is done metabolically speaking in the biological world, it requires energy. But then outside of the biological world, anytime the wind blows, anytime the sun shines, anytime the rains fall, that is energy being used, okay? And it's the ability to do work. Now, living things need to grow, develop, move, and perform voluntary and involuntary body processes. That's called metabolism. And our metabolism requires energy. It's one of the reasons that we consume food. So I tell you all this because I want you to know that I expect that kind of an answer to be put in there, okay? Please make sure that you are doing that. Basically, the universe consists of two things, matter and energy. Every single thing you've ever experienced physically in this universe is either a form of matter or a form of energy, or more than likely a form of matter that is using energy, okay? Energy makes matter move and changes it. Different forms of energy include things like thermal energy, warmth, radiant energy such as light, electrical energy, you know what electricity is. There's nuclear energy, there's sound energy, there's just all kinds of energy. The world runs on energy. The universe runs on energy. Energy allows us to get out of bed in the morning, and we also use energy for all of our daily activities. And by the way, we get all of our energy from the foods that we consume. We are what's called heterotrophs. And this creates an interesting process about how do we get energy, because what do we eat and where does its energy come from? Is a very good question. Almost every biological process we can think of requires energy. But what is energy? Energy itself is a little difficult to define, but its technical definition is the ability or the capacity to do work. And I want you to think about, having to go to work, if you have a job. I'm talking about at your cellular level, your cells, in a microscopic level that's so hard to see with even a microscope, but there are still things there doing work. And whenever you perform a task in your body that you're aware of, such as moving or digesting or breathing or whatever, that's a combination of billions of cells performing a task. Right now I am making energy, I'm making noise with my body, and that's requiring my cardiovascular system, it's requiring my brain, my nervous system, structures such as my larynx. And all of those things are thousands and millions and billions of cells working together using energy to perform a task, okay? And that's how my body works. A plant works differently, a mushroom works differently, a bacteria works differently, but they all do the same thing. They use energy to accomplish tasks. A couple of things are some forms of energy. You've probably learned this 1,000 times. Let's just go over it again real fast. We can break energy down into two kinds, kinetic and potential. Potential energy is what we call stored energy. It is when we've taken matter of any form and we've actually stored energy inside of it. And as a result, that energy is ready to be released. One of the classic examples is some type of a structure such as this ball on top of a hill. In order to get that ball to the top of that hill, energy had to be used. But with a very, very small amount of energy applied to it, you can release a lot of energy by the ball rolling down the hill. And it will go fast this way or slow this way, but by the time it gets to the bottom, the same amount of energy has been released, just depending on time. But potential energy is that ball will sit there from now until forever and forever and forever, until something acts on it and has it moves. So right now it has incredible potential energy. And then once that energy is released, of course, we call that kinetic energy. Your body is full of potential energy. It's in the form of fats or sugars or oils or waxes, all these forms of energy that we store. We store energy in our body in these ways, in the form of chemical bonds. And chemical bonds are these bonds usually between a carbon and a hydrogen, and my body is very good at breaking those bonds and releasing the energy. Sugar, for example, is a huge amount, an unbelievable amount of carbon and hydrogen bonds, and as much carbon and hydrogen bonds as there are there, I can release that energy. But guess what? There's a molecule that has even more energy in it per molecule than sugar, and that would be a lipid, like a fat or an oil. Fats and oils have even more carbon and hydrogen bonds. It takes our body a little bit longer to release those energies from those lipids, but they're there, and they're just sitting there waiting to be used. I happen to have a particularly large amount surrounding my belly right now, and that's just fat stores that my body can use for energy, so we can store it. But I have to have the kinetic energy. Once that bond is broken, that energy is released, and I do work with it, because that's how every bit of my body works. And if I ever run out of these chemical bonds, then I'm going to die. And so we consume potential energy, we digest the potential energy in the form of these chemicals, and we either release them or store them for our use. Then there, of course, is the idea of the kinetic energy. Kinetic energy is when that energy is being used. Quite often it's spoken about in terms of movement or motion, but it can be the release of heat, it can be a release of electrical energy, it can be a release of good heavens, there's all kinds of energy releases that can happen. And as like I said, even though it's technically an energy of motion, I'm making a lot of sound right now with various structures in my body, and as a result, that's sound is a form of energy. And so once we release that potential energy, it turns into something: heat or sound or movement, or I don't know what think about things that produce other, like what are the things that glow in the dark, like jellyfish or eels or something that release other types of energy. Jellyfish can glow in the dark. That's energy they're releasing. Eels can release electricity. They generate that by breaking the bonds of this kinetic energy found in these chemicals and turning it into electrical energy. An interesting thing, you may find this stupid, but for instance, I don't know if you've ever seen a flashlight that you can charge by winding it up. They were the big thing about 10 years ago. You get a wind-up flashlight. Well, the motion it takes for your body to wind that flashlight comes from breaking the bonds in those chemicals that we talked about, and then we transfer it into the energy in the flashlight, which creates light. So energy can be turned into other forms of energy, and that happens all the time inside of our bodies and outside of our bodies. And this is basically how metabolism works. My entire body is geared towards grabbing this energy, releasing this energy, and doing jobs. Now, not necessarily talking about living things, although a lot of this type of energy is found in living things. Mechanical energy, chemical energy, thermal energy. But right now, let's just talk about energy in general. Okay. Now, mechanical energy it's kind of defined as the sum of an object's kinetic and potential energies. Mechanical energy is when a structure is it's storing some energy, and it's making some energy, it's releasing some energy, or it's storing. It's mechanical energy is all about movement. Okay. Now, I want you to understand something. While this says machines, when you move, you're using mechanical energy. Okay, by walking, you are using mechanical energy. By talking, by breathing, by swimming, by, God, I don't know, whenever your body is at movement, whenever your body is moving on your own, when you're moving it, that's your mechanical energy. Now, if I get into my car and move it, then the car is using the mechanical energy. Okay. Of course, nuclear energy is one of the newest forms of energy we've discovered on Earth, even though it's been almost 100 years since we discovered it. But we can split the atom and release energy from an atom and use it to produce energy. There's two kinds. There's fission and fusion. Fission is the kind of energy we've had around for a long time, and it releases a large amount of energy, but it does consume the fuel, whether it's plutonium or uranium or something like that. There's this other stuff though called nuclear fusion, which is what happens in the sun, and we've been working really hard to try to make that happen here on Earth, to create reactors that instead of using fission, they use fusion. Fusion reactors won't run out of fuel as fast, and they produce a ton of energy, and they can actually release interesting things such as helium. That's a byproduct of the fusion reaction, and we, by the way, are very low on helium here on Earth because we don't have a process to create helium because it's an element. But through this process of nuclear fusion, we produce energy, and then a byproduct, interestingly enough, is helium. Now, this kind of energy is rarely found in our, we don't do this. Living things don't do this. Okay. In fact, this can be kind of damaging to living things. But if done right, if controlled right, I believe in nuclear energy. I think we should be building nuclear reactors like crazy. It's going to provide energy in a starving world. But that's another argument for another day. But nuclear energy is a type of energy. Chemical energy, this is one of the biggest things we do in our bodies. Chemical energy is a form of potential energy stored in the chemical bonds of atoms that make up molecules. Now, we've already talked about this, so this should be fresh. But again, chemical energy is released in humans literally in all living things through a form of digestion. And then the energy is released and we use it. There's gravitational energy, that's like this water tower. God, they found an ugly water tower, didn't they? But this water tower, you put water in the top of this tower and it sits there. By moving the water up into the tower, you're taking kinetic energy in the form of the moving water. You're putting it in the top of this tower and letting it sit there. Now it has potential energy. And if I go to my house and I'm attached to this tower and I turn on the faucet, then I'm letting a little bit of that potential energy turn into kinetic energy by giving me water pressure. And that's just one example of gravitational energy. A ball sitting on top of a hill, a bird sitting on the top of a tree. That bird has gravitational energy, and if it wants to then drop out of that tree and start flying, it's using gravitational energy for a while to get it started. Thermal energy is, in humans at least, is kind of a result of what we do, and a lot of living things, especially animals, produce a lot of thermal energy because our metabolisms, we use so much energy. Thermal energy is a byproduct, but it is also the most crucial part of us. But it is a form of kinetic energy, and it usually comes, with us at least, in the forms of breaking down these molecules, and the process of using the energy creates heat. What really happens with thermal energy is that the atoms start moving faster. They start to vibrate, like a solid will start to vibrate. It vibrates enough, it'll turn into a liquid. And liquids there's so much energy that the atoms are actually moving around, and they get even more energy, they can become a gas. And you guys have studied that before, but that's thermal energy, and it has an awful lot to do with biological life. Electrical energy, yes, there is electrical energy all in living things. It is kinetic energy. Storing electrical energy is very hard. Batteries do not store electrical energy. Batteries store chemical energy, and then the things we put batteries into convert that chemical energy into electrical energy. Okay, so we don't normally store electrical energy. There are things that can do it, but it's fairly rare. But using electricity is a very common thing. It's been going on for billions of years. And all living things to some degree use a small amount of electrical energy. You do. You actually generate an electrical field with your body. Your brain generates an electrical field and produces radio waves. Isn't that weird? But every time you use a nerve for something in your body, there's an amount of an electrical wash that happens through your body, and the energy that, among other things, it's chemical, but it's also electrical, and that's how your nerves work. Your heart is constantly being hit with a wash of energy across the AV nodes that causes your heart to beat. That's what causes your heart to beat, is electricity. That's what causes your muscles to contract, is you're actually sending electricity. Okay. And then finally, radiant energy in the form of light or microwaves or radio waves. This is all types of energy, and like I said, it's used. Of course, light is important to us. Unless you're visually impaired, you use light to see with. The sound that you're hearing is a form of radiant energy, and so you use your ears to hear. And so this electromagnetic radiation, it's kind of amazing that we've evolved structures that allow us to be able to see and hear things. But imagine what it's like to not be able to do that. And if you have a visual or hearing impairment, bless your heart, But most people that have these impairments have figured out ways to survive and do well uh, without it. But it's pretty amazing that if everything's working for you, that you have an ability to see. The eye is one of the most incredible things in all of biology. Those are the types of energies. There's more. You can, like, some of these are large groups, like radiant energy covers so many other kinds of energies, but these are the big groups, and some of them do apply directly to living things, and some of them, it's a bit of a stretch, but at least you know what they are, right? And every single one of them is some combination of potential and kinetic energy. Now we get into something called thermodynamics. Thermo means heat and dynamics means change. So thermodynamics literally means a change of heat, but in this case thermo really is kind of referring to energy. And so what we're going to be talking about with these ideas of thermodynamics, of which there are two main things we're going to talk about, is the idea that energy can be moved or changed or moved around, changed, I don't know how you want to put it. But there's an interesting couple of laws that make it important, and they apply to everything in the universe, from a car to a cow to a cliff to I don't know what else starts with C, to clouds. But they do. There are two basic laws: the first and second law of thermodynamics, and you really need to know them at a basic level. Okay, we're going to start out with the first law of thermodynamics, which is what this particular picture is trying to show you. I don't like this picture because I think it's a seesaw when I first see it, and I'm like, well, okay, what are you trying to say? But what they're trying to say here, this is really a balance, and they're trying to say that the energy before has to equal the energy after anytime something's done. Anytime energy is used or transformed, you have to have the same amount of energy coming out as going in. And a lot of times people try to argue that, oh, no, there's more energy coming out, or no, I put more energy in and less came out. But the first law of thermodynamics always says that the same amount of energy has to be there before and after. We don't create energy, we don't destroy energy, we very simply move it or change it. Okay, and so think about that flashlight I was telling you about earlier that you wind up. That energy, the amount of energy coming out of that light, had to equal the amount of energy I was putting into it by, I don't know, whatever muscles I was turning. Now, while that's very interesting, the light is not the only thing that was the only form of energy that was being produced there. There was heat energy caused by the friction of the device, and there was even sound energy caused by it making a sound. And so all of those energies add up to the amount of energy I put into it. And sadly, one of the problems with thermodynamics, and this is where we come to the second law of thermodynamics, is that usually energy cannot go in a straight line, and it's not very efficient when we transfer it. I can't go straight from my body to light. Generally I have to lose energy to make that happen, for example. And so the second law of thermodynamics talks about something called entropy. Before we get to the second law, I want to talk a little bit more about the first law. The first law, as applied in the human body, for example, it goes like this. This beautiful lady is eating some food, and there's energy in the food, and that energy then goes into her body. Now, one of two things is going to happen. Either her body is going to harvest that energy and use it or store it, or her body is going to release that energy in the form of heat. Either way, all of the energy that's found in this bowl of food is going to go through her body, okay, and then come out the other side. Either it'll come out in the form of heat, which is a lot of it, or it'll be used to build her body, or it'll be used to maintain her body, and that's, it'll be able to be used to move her body, heal her body. I mean, there's all kinds of things that it's done with, and in almost every case it then leaves in the form of heat, believe it or not. But when you add it all up, and it would just be like a plus and a minus, but if you take all the energy in here, you could see, if you had an ability to measure it, how it would all come out of her body. Okay, that's the first law of thermodynamics, is however much energy goes in has to come out. It's a done deal. Now, it doesn't have to come out fast. It doesn't have to come out today. It can be saved and stored for later. Our bodies are very good at that. It doesn't have to come out in the same form it goes in. Here it's going in as chemical energy, and it's probably going to come out as heat energy. But basically, the same amount of energy going in has to come out. That is called the first law of thermodynamics. The second law of thermodynamics tells us how inefficient this process is. Almost always, every time, we lose energy just to inefficiency. Okay? Think about this. The amount of sunlight hitting a plant, the amount of sunlight hitting the earth is way more than the amount of sunlight that is put into plants and used. Okay, and so it's very inefficient. The amount of energy that goes into a plant and then you eat the plant, that amount of energy is way less than it was absorbed, because the plant used it for metabolism. The plant lost it to inefficiency. The plant used it to do other things, just to keep itself alive. If you were to count the amount of energy that the plant absorbed, and then you eat the plant and count the amount of energy you absorb, the amount that you got is going to be way less than the plant got. In fact, almost as much as 90% less than the plant got, because the plant used the other 90% for various things, or it wasted it. This is the second law of thermodynamics, and the second law states that it's called entropy. It's disorder in a system, and it accounts for inefficiency. And basically, every system is losing energy just to inefficiency. That's what the second law of thermodynamics says. And so we're never going to get back more energy than we put in. In fact, the second law says we're never going to get back the same amount of energy that we put in. We're always going to lose energy whenever we convert or move energy around. Now, in case you didn't notice, I jumped ahead, but with all that understanding of what energy is and how energy moves and rules about moving energy, let's talk about how it works in an ecosystem. Okay, all living things depend on energy. You do, the grasshopper does, my pet dog does, the trees outside, the bacteria living on my body, they all require an energy. And in so many cases, you can basically say everything, although there are a few examples, but almost everything uses the sun for the energy. The energy you're using right now is sitting in your house or wherever you are. I'm sitting in my house. And I'm there's a roof and then another roof underneath that, like my ceiling in my bedroom or my office. There's insulation. I mean, there's so much stuff between me and the sun right now, and yet I'm not anywhere near the sun. There's actually one little sliver of light I can see right now that's actual direct sunlight. I'm not getting any energy from the sun right now. Okay, but what I did do was earlier today I had a piece of bread. And that piece of bread is made out of something called wheat. Wheat is a plant. This wheat probably grew somewhere out in the Midwest within the past 6 months or so. The plant grew, and it created a structure, a seed called wheat. That wheat was harvested. Somebody then took it, ground it up, did some amazing chemical stuff to it, and turned it into bread, which I ate and my body tore the energy out of and is now using. Okay? Here's the thing. My body is using sunlight energy, but it's using sunlight energy that was stored 6, 8, 10, 12 months ago. I found some sugar that I had put into a container from, probably 3 or 4 years ago. And the cool thing about sugar is it never goes bad if you keep it stored airtight. And I used it. And I mean, that was sunlight that hit the earth 4, 5, 6, 7 years ago. Who knows? But it can store for forever. That's potential energy, until my body releases it in the form of kinetic energy. But that's sunlight. Okay, sugar, you can think of it as just stored sunlight. It's kind of crazy. But all living things use that sunlight, with some exceptions, I know, but let's just forget those for now. How do I get sunlight to power my body? And the answer is called the food web. Ecosystems there's no living thing ever exists by itself. Instead, they all work together. Now, here's a picture of an ecosystem, and you can see, everybody's happy. Look at the mosquito, it's so happy. Look at the duck and the frog and the fish and the bug, and etc., etc. But the truth is all these things are kind of, they work together to create the ecosystem, but they're not working together like friends. Okay, they're not buddies. Everything here is eating something else. Okay, and so what's really happening here is that you have all of these organisms living in this ecosystem, and the energy is being put into the ecosystem and then passed around. Okay, and everything here eats something else with the exception of the plants. So ecosystems consist of two things, both biotic, that word biotic there, it means living, and abiotic, meaning non-living factors. There's all kinds of biotic factors: the temperature of the duck, the number of fish, the chemicals found in the snail. These are all biotic factors. The abiotic factors are the depth of the pond, the sand that makes up the bottom, the temperature of the water, how fast the wind is blowing, whether or not the sky is dark cloudy or bright and sunny, sunlight. These are all abiotic factors. And they all work together to create the ecosystem. And like I said, the sunlight goes in and then it moves through this ecosystem until it comes back out as a form of heat. And every time it moves from one organism to the other, most of the energy is lost because of the second law of thermodynamics. So ecosystems are a great way for us to study how energy moves around. Now, what you probably didn't see there, unless you looked, you may have noticed, but there's several food chains, in fact food webs, in that ecosystem. Now, all a food web is a bunch of food chains just all kind of put together. So we like to look at food chains and food webs. Today in our tutorial, all we're going to really look at is a food chain, but a food chain shows you the first law of thermodynamics, which is energy isn't created or lost, it's only moved. Okay, and then the second law of thermodynamics, which is that from every time you move or change energy, you lose a lot of it. And so imagine these right here. These are called the primary producers. Now, in an aquatic ecosystem, they don't always look like plants. In fact, a lot of times they look like single-celled organisms or clumps of single-celled organisms. But these guys are absorbing the sunlight and storing it into their bodies. And then something comes along and eats them, like these things called primary consumers. These primary consumers grab these things and eat them, pull the energy out of them, and use them for their own bodies. These guys are like, no, not me, but whatever. Welcome to the way the world works. And so these primary consumers eat these things, and they use the energy that these things absorbed. Now, these things weren't like, okay, I need to store up energy for that shrimp that's going to come along and eat me. No, they had their own plans in life. They were going to grow and divide and grow and divide. But nope, here comes along a shrimp or whatever these things are right here, these pill bugs or whatever, and they eat these things and they get the energy from them. And these things are like, okay, whew, I ate. Now I get to have energy. I get the energy. I had to eat all these things to get the energy, but there we go, I got it. Now I can live my life and I'm going to raise my children and retire. But nope, along comes a secondary consumer and eats a primary consumer and gets the energy yet again. And now the energy for this, every bit of energy this secondary consumer gets came from eating a primary consumer, and all the energy it got came from eating producers, and all the energy it got came from the sun. Then we go on to the tertiary. Tertiary means third level. These tertiary consumers eat the secondary consumers that ate the primary consumers that ate the primary producers that absorbed energy from sunlight. And then you got your quaternary consumers that ate the tertiary consumers that ate the secondary consumers that ate the primary consumers that ate the primary producers that got the energy from sunlight. Believe it or not, this shark, every bit of movement and metabolism it ever does in its entire life, ultimately through this chain of energy transfers, the energy for it came from the sun. Kind of crazy to think about, right? But here's the big problem. Every time the energy is transferred, about 90% of it is lost. Okay, so if I have energy here, most of the energy here is going to be lost, and only a little bit is going to go here. And all the energy that's here, most of it's going to be lost, and only a little bit goes here. And of all the energy that's here, most of it's going to be lost, and it's going to go here. And by the time you get to the shark, imagine how much of these primary producers you have to keep that shark alive. And we're talking about a huge amount to keep a quaternary level alive. It's pretty awesome, pretty crazy really if you think about it. That's why most living things on Earth that's why most heterotrophs, which is everything that's not the primary producer, these are autotrophs, everything else is heterotroph, but most heterotrophs really live as a primary or secondary consumer because it doesn't take as much land or sea or whatever to keep these things alive. If these were humans, primary consumers would be your vegetarians, okay? But if you think about it, most of us exist either at the secondary or the primary level. We're eating vegetables or we're eating things that ate vegetables. We are either primary or secondary consumers. Only rarely do we go up to the tertiary or the quaternary level. Because we're omnivores, we can exist at any level past primary producers, but most of the time we spend here or here. I mostly eat vegetables and I eat some meat or products from meat, and that's really it. And most of the meat that I eat is generally an herbivore, so it was a primary consumer eating this, and then I ate it. Very rarely do we eat stuff we're third or fourth level. We do, but it's rare. Now here's all of that I just told you, but in not a graphic form like pictures, but in just more of a chart. But this is called the food pyramid, and this very clearly shows the second law of thermodynamics. The producers, such as in this case, they're talking about green peas and huckleberries. Okay, those are plants. They're getting energy from the sun, and this 100% shows all of the energy available from them that they have successfully harvested from the sun and then stored or used, typically stored, okay? It does not represent all the sunlight energy because they missed almost all of it. There's something like 1,000 times more sunlight that they did not get per square meter versus what they did get. And so the process is inefficient all the way down. But here's the thing. A primary consumer comes along, such as a slug, and comes along and eats some of the green pea plant, right? Of all the energy available to the primary consumers from the producer level, only about 10% actually goes. Now this isn't exactly 10% every time. It does go up and down. Some things are more efficient than the others. But on average, it's about 10%. 10% of the energy from the producer level actually makes it into the consumer level to be used for metabolism. That's growth, that's development, that's maintenance of their bodies, that's movement, all of their metabolism. Okay, the rest of it, 90% of the energy that was stored by the producer level is lost due to heat. Okay, now along comes a frog and eats a slug. So again, there was energy available at the primary level that the frog consumed, but of all the original energy available, only 1% now is moved into the frogs. That's 1% of the energy here. That's 10% of the energy coming out of the consumer level, but only 1% of the energy from the producer level. We're showing that to you to show you how inefficient the process is. 100% of the energy here, only 10% moved in here, only 10 more percent or 1% of the original moved to here. If a snake eats a frog, it only gets 0.1% of the energy originally available. And then if a heron eats a snake, then it only gets 0.01% of the energy available. Can you imagine that if you're a heron, how much energy, how much of the producer level it must take just to keep you alive? Okay, if I need to get this number up to 100%, I've got to have, what is it, 10,000 or 100,000? Let's just say 10,000 times as much producers to keep this heron alive. And so it's very interesting to note that it takes a lot of the producer levels just to keep a food chain going. Now this doesn't work for necessarily just energy. It also is for what we call biomass, or the matter that's moved along. Because when I eat something, I don't just get energy from it, I also get matter from it. And again, the numbers work out to be about the same. Only about 10% of the matter that is consumed at the producer level goes into the consumer level, the primary consumer level, and stays there. The rest of it is lost to metabolism and just sent out as waste, and then another 10% and another 10%. And so you can imagine how many tons of producers it takes just to keep a heron alive. All right, and the same thing with numbers. And for some reason, it's just so funny how it works out. But 10%. If I have one heron, I'm going to have at least 10 snakes, 100 frogs, 1,000 slugs, and 10,000 green peas plants. Okay, that's just to keep it alive. Although, you know, it takes even more than that. So the thing to note is that every time we add a level, primary level, secondary, third, fourth level, it means that the producer level has to get bigger. Interestingly enough, the producer level in a lot of cases can exist all by itself. It doesn't need any of the other levels. Okay, the primary level needs a producer level, but it doesn't necessarily need it. Sometimes it does, but sometimes it doesn't need these other levels. The secondary level needs the primary and producer levels, but it doesn't need the tertiary or the quaternary levels necessarily. But we can keep adding, because something eats the heron, and then something eats that, and something eats that, and every time we go up, okay, this base right here has to keep getting bigger and bigger and bigger just to support that. Now, strong ecosystems like the Everglades and Lake Okeechobee, they are very diverse, very energy rich ecosystems, so they can handle these higher levels. But some ecosystems like deserts or alpine ecosystems just don't have the energy available. That's why you don't see very many levels there. Now we're going to switch a little bit. Let's talk about energy, and not just energy in metabolism and living things, and just basically how the earth would be without humans. Right now we're going to switch to how humans use energy, and we use a lot of energy, and I'm as bad as anybody. You know, I turn on the air conditioner in the summertime when it gets hot. You know, I'm like, well, I guess I could save the environment a little bit, but instead I'm going to turn the air conditioner down to frozen and enjoy myself. That's why I went to college. So humans use a lot of energy. Okay, we mine it from the earth or in other forms, renewables versus non-renewables, And and then we have factories, we have power plants, we have production facilities, we have vehicles, we have our homes that use electricity. I mean, we have so many ways that energy is used on the earth. Now the earth has a lot of energy in the form of things like petroleum or coal, or natural, renewable resources like trees and things like that. But the problem is that we're starting to get to the point to where humans are creating this enormous energy demand. I mean, it is unbelievable how much energy that we're using, and it's only really happened in the last 75 years. Humans have been around for a long, 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 long time, and only in the last 75 years or so have we started to really, really ramp up our use of energy. And today we use so much energy, it's just unbelievable. And like I said, I'm as bad about it as the next guy. Now, the problem is this. A lot of our energy comes from what we call a non-renewable resource. It's this thing that's not going to be renewed anytime soon. I mean, we're talking about billions or millions of years before we can renew it, such as fossil fuels. Okay? The Earth has an abundance of fossil fuels. We still have a lot of fossil fuels in things like coal, oil, natural gas. And we use it like crazy. I filled up the tank of my Jeep this morning. I'm running natural gas when I run my water heater. The power plant to run my house is probably a coal-fired or natural gas power plant. The one they're building north of town around Fort Drum is a natural gas power plant. These are all non-renewable resources. We pull them out of the ground and we basically burn them. And that, it gives us electricity. It lets me have a hot bath. It lets me hop in my Jeep and drive wherever I want to go. I'm flying to Seattle this summer on a jet that runs off of fuel, natural, out of petroleum. But the problem is we're going to run out. It won't be tomorrow. It won't even really be in my lifetime, but we're going to run out. And so we got a problem. If we don't figure out how to do all the things that we're doing today in some other way without using these fossil fuels or these other non-renewable resources, we're going to run out. There's another problem. Using these non-renewable resources is causing some damage. Now, I am a pretty conservative person. I'm not the typical tree hugger science teacher like you're probably picturing. But the truth is even I will admit that we are putting a lot of stuff into the atmosphere that wasn't there just 75 years ago, and it is causing a change in the climate. I don't want to say climate change, but it is causing a change in the climate. Things are happening, and it's because humans are using so much of this non-renewable stuff. That's why renewables are kind of exciting, and we're finally getting to the point where we might be getting to where renewables might be doable. Chevrolet announced that by the year 2030 or 2025, they're no longer going to make cars that run off of gas. It's all going to be electric vehicles. Every electric vehicle from Chevrolet. It won't be long before Ford and Dodge and everybody else is going to be right behind them. In your lifetime, you may actually get to the point where you no longer see gas stations, at least not stations that sell you gasoline. They'll let you plug in your car and charge it up. Okay, well, the problem with that has always been, where does the electricity run to charge that up? Usually it comes from a natural gas power plant. That's where it is today. But believe it or not, solar, and I'm a huge fan of solar, believe it or not, solar energy is getting to the point where we're going to be able to charge our cars and our trucks and stuff off of solar panels. And so we will literally be driving using converted sunlight. It's a crazy thought, but the day's coming. The cost of solar panels has come down so much in the last 25 years. This panel used to be $1,000. Now it's $80, for example. Okay? And when it gets that cheap, now I can put these panels at my house and just plug my Jeep into it. If my Jeep were electric, just plug my Jeep into it and then drive, and I won't be using any non-renewable resources. I'm excited. I can't wait. There are people already doing that. I'm going to run my house off solar. I'm going to run my business off solar. Now, there are some things that won't be able to run off solar. You're not going to run an airplane off solar. You're not going to run a rocket off solar. But if the less of these non-renewables we use, the better off the Earth is going to be. I just firmly believe that, and I hope you're thinking that way too. So there are all kinds. We've already talked about fossil fuels. You know what that is. Now, fossil fuels aren't necessarily made out of dinosaurs. Everybody thinks they're made out of dinosaurs, but I want to clear that up. Fossil fuels are mostly made out of plants that were around at the time of the dinosaurs, okay, and all this plant life. And there was a lot more plant life back then than there is now. But all that plant life, when it died, it landed on the ground, and you can go outside and see dead stuff on the ground by your house. It's everywhere. But that stuff builds on top of each other, and after millions of years, it gets crushed down into things like coal, oil, or natural gas. This isn't dinosaurs. There may be some dinosaur material in there. Surely there has to be some, but it's mostly plants. And that's what people need to know about fossil fuels. This is a non-renewable resource. And yes, it is renewable, but it's going to take several million years to be able to create coal out of the trees that we have today, for example. We just don't have that kind of time. So for all intents and for all purposes, this is non-renewable. We're going to run out of it, okay? Water is a renewable resource, okay? So if we build a dam, and when we let the water flow through that dam, we let it turn a mechanical device called a turbine, we can turn that into electricity. And there are lots of places on Earth that use hydroelectric power. Water is a great resource. There are other ways to harvest water as well besides a hydroelectric dam. All of them have their problems. Dams disrupt rivers. They change the flow of the river. They turn a flowing river into a lake. And so they create problems, but still it's probably in the long run better than burning fossil fuels. Radioactive materials. This is my second favorite. Radioactive materials, nuclear energy. Nuclear energy used to be a problem. Back in the 70s and 80s when I was a kid, oh my God, we were all going to die because these nuclear reactors are going to melt down and we're all going to die. But the truth is today, we've got the science and we've got the construction of these things down to an art. We can build them and they're safer than anything else. Something like 0.01% of human deaths from nuclear energy as compared to coal. Something like for every one person that dies from a nuclear power plant of some form, there's like 10,000 people that die from coal. Nuclear power is way, 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 way more safer than just about any other form of energy up here. And it can give us a lot of energy fast. And there's plenty of fuel. We're not going to run out of radioactive material. This is where I picture most of our energy coming from in the near future. Wind, it's everywhere. Wind blows everywhere. It's actually a form of solar energy, believe it or not. Wind is just the air moving caused by the heating of the sun. It's good. It works. We're still learning how to make it happen. The wind can produce a lot of energy fast. There are some problems. They're ugly. They make a lot of noise. And birds hit them. That's just a few of the problems. And so every day at the base of this tower, somebody walks by and counts the number of birds that are dead at the bottom, because in a 24-hour period, this tower is going to kill some birds. And so will that tower, and so will that tower, and that one, and that one, and that one, and that one, and all those back there. That's a lot of dead birds. And it causes problems, but it produces a lot of electricity. So what do we do? I mean, do we not build these things to save a few birds? Or are they saving these birds so important that we don't need these? We'll talk about that in the end. Here's one for you. The Earth's internal heat, geothermal energy, is a really neat form of energy. It doesn't really do much damage, but it's rare. It's hard to get to. It's hard to harvest. It's there, and if we could ever really learn how to use it, man, we could do a lot. Okay, and it's renewable. By the way, let's see. Non-renewable, renewable, kind of non-renewable, renewable. This is renewable. All the rest of these are renewable. The only non-renewable up there is coal, oil, and natural gas, the fossil fuels. And the radioactive materials are kind of not renewable, but everything else is renewable. So Earth's internal heat is a form of renewable energy. And it works. And it's great. It's just kind of hard. The engineering for it is hard to make it happen. So there's not a lot of this going on. But it could be. Okay. Sunlight, my favorite. Solar panels. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 24 panels here. 25 years ago, this would have cost $24,000 to make. Now it costs about $1,500. Okay. One of these right here, a panel this size, could run my house. This many solar panels, 24 panels, could run my house and provide me all the energy that I need, including air conditioning. You know, with some changes, like my house is old, my air conditioner is old, but if I build a new house with a new up-to-date insulation, up-to-date electronic equipment, you know, good refrigerator, good TV, all that kind of stuff, and I put in a good air conditioning system in my house, I could run my house off that right there, $1,600. Now that's not all. You got to buy some batteries and some other stuff, but there are people that are building houses today. They're not even hooking it to the power to Glades Electric or to FP&L anymore. They're just hooking up solar panels. And we're going to get to the point where that's even more. You get another one of these, that'll charge up your truck. 2 of these is all you need. Charge up your truck, run your house. Yep. What do you think about that? I'm telling you, I love solar. Okay. Biomass is interesting because biomass is something we can grow, and it is renewable. And yeah, we're chopping down trees. Yeah, I know, but just hold on a minute. Farming trees is not as damaging to the environment as you might think, and we can grow these trees rapidly. We can use the biofuel to create energy, whether it's heat to generate electricity, to cook with, etc. We can create something called biogas, which you can actually run cars off of. We can decompose it and let it produce methane, which we can then use as like a natural gas. There's so many things that we can do with biomass, and that's probably my 4th favorite one of these up here. I think it's very useful. I think it has a place for us to be mining this biomass, but it's still kind of in its infancy, and so we're still kind of like, yeah, it's just not as good as sunlight, and it's definitely not as good as nuclear energy. The last one's ethanol. Ethanol is kind of funny because right now ethanol takes a lot of energy to make, and while it is technically carbon neutral, it's not as good as people think. Believe it or not, you're using this like crazy. You go to the gas station, put gas in your car, you may or may not notice, but it says may contain as much as 10% ethanol, and this is what it is. Now, all ethanol is we take sugars from things like sugarcane or corn, and we let these little guys digest the heck out of that sugar, and they do it without any oxygen, and they create a lot of ethanol. Ethanol is actually just drinking alcohol. Okay, methanol is just like rubbing alcohol, but to create this ethanol, okay, it's flammable, and we can put it in a vehicle and run it. It's crazy. And there are cars today that can run off of 90% ethanol. They just need a little bit of gas in it to make it run. Is it efficient? Does it work? The jury is still out. There are people who think that ethanol is just a waste of time. Not sure about this one. I'd like for ethanol to work because it means we can farm our energy, and our farmers can grow. I'm a huge ag proponent, as you guys know, and our farmers could grow energy. And I love the idea of energy crops, but it takes a lot of energy to make this ethanol, so I don't know. And so that's all the forms of energy. That's all the types of energy that we can use. And as you've seen, energy is all around us. It's vital to life on Earth. It allows modern society to function. You need energy. All living things need energy. But I'll tell you something interesting. Okay, I want to go back here. All of these things provide us with energy, but what we didn't talk about was, what if we just use less energy? What if we turn the lights off? What if we didn't drive as far? What if stupid science teachers didn't take vacations to Seattle in the summer? Do you have any idea how much energy it's going to take for me and my family to go on vacation this summer to Seattle? But if we use less energy, then we have to get less energy. We'd have to use less fossil fuels if we drove less distance. If we turn the thermostat down and turn off the lights, and maybe didn't take such long showers, and maybe didn't have such inefficient vehicles and inefficient appliances, okay? And if companies and businesses would do more about conserving energy, we could keep going the way we're going for a lot longer, but we're very wasteful. And that's something that's important to know when it comes to this kind of stuff. We are very, very wasteful of this energy, and it's better if we, instead of wasting it, if we're smart about using it and can start using engineering and science to come up with better ways for us to do the things that we need to do or want to do, but with less energy. Well, that's it. It's taken me 49 minutes to do this, and I hope you enjoyed it. This is some good stuff, and we're going to be talking about energy and biological processes more in the next 2 modules, but something you needed to know, this idea of energy. Alright, that's it. Good luck. Let me know if I can do anything for you. Bye.